Go again, do that move for me. So here's the potassium. Now, okay, hydrogen gets kicked out, oxygen takes the electron. Potassium ion and hydroxide ion are produced. Negatively charged hydroxide, head and you show that reaction. Excellent, eh? Good? Yep. And we're going to go over to this thing. I think we forgot to say that this was our after picture. I know. Did you get the after picture?
Yeah.
Okay.
Now it is.
Okay.
Got that.
When this oxygen is attracting potassium's electron, okay, it moves there, it bumps out that hydrogen, and that electron moves to there. That whole thing that Miss Webb just did with her hands, that movement of that electron and the bumping out of the hydrogen is when we saw the sizzling, the flames, and that sort of stuff. We saw the signs. When the electrons are moving, we see the signs. Okay? So when we look at number 1, bubbles of gas appearing, which one of these things? So if I'm going to pull my other waters away, this was my reaction that is now complete because all shells are filled. Which one would be the bubbles of gas? Which one would represent that? Yep.
The hydrogen.
Yes. It would be represented by this. And the chemical formula for that is H2, and it is a gas. So that's number 1. Those are the bubbles of gas appearing. Yeah?
Does the hydroxide ion have like an effect, like visually?
Yes, it does. So heat and or light is produced. So the movement of that electron generates some heat. And the fire that you see is this gas actually igniting. Potassium, you no longer see it in the bucket when you're done. Right? It's gone. So now we got to talk about number 4. Okay? And what I'm going to model for you here is I'm going to talk to you about how material with new properties is formed, and really I'm going to talk about an experiment I can do to determine that there's a hydroxide in there. Okay, so there's the test I use is called a pH test, and I'm going to use pH paper. And the pH paper will change color depending on what's in the water. So I'm going to take this pH paper and I'm going to stick one in the water. Okay? So that is material with new properties is formed. So you need to add that to your signs. Okay? The pH paper turned green in the reaction side. The one where potassium, sodium, and lithium were reacted. And in pure water, it stays orange.
We are now ready for the great.
So the story of how we tell exactly what happened, because what we did was we broke down that chemical reaction into steps, is we do this by writing out equations. Okay? And we're moving into the criteria for what you're going to write in your recipe book. So the first thing we're going to write is we're going to describe what happened, the story of using a word equation. Okay? this is my short form. I just need less space, so I have a little bit of a smaller magnet there. The before is what we started with. And I'm just going to do this one. So we started with, the word is, we started with potassium, and we added the potassium to water. We included an arrow. The arrow is actually, funny thing how this works, nice and hand in hand. Whenever we did arrows, it was the during pictures. So that arrow is still representing the during. The reaction is happening. This stuff is now gone, and it becomes my after stuff here. Okay. So my after is, I form my, where did my potassium go? There it is. I formed a potassium ion, a hydroxide ion, and a hydrogen gas. Okay? I'm going to tell you a little bit about the way these guys behave. So, Katie, we need to have this zoomed in over here. I've talked to you already about a polar covalent bond. Okay? So we're going to do a scribble picture because these actually, because this is a positively charged particle and this is a negatively charged particle, they have an attraction to one another. Okay? So I'm just going to do my very simple CVR. That's potassium's core. It's lost its valence shell, so I don't draw another ring. Water. Sorry, hydroxide ion. That's our hydroxide ion. So the electron, so here is potassium's electron. Still not right. That's better. Yes? That looks proportionate. I've got the proportions correct. That's important. Okay? So here's the electron that oxygen took from potassium. Okay? So in our script, we know it's going to spend a lot of its time around the oxygen. Do you see the difference between that scribble picture and the polar covalent bond scribble picture? The polar covalent bond one these are hydrogen's electrons majority of the time, but hydrogen has a higher electronegativity, so it still is able to grab a hold of that electron. Can you see the difference between these two? Yes. So this is called a polar covalent bond. This bond is called an extreme polar covalent bond. So in water, a polar covalent bond, this bond is an extreme polar covalent bond. Hydroxide, I asked you to make notes on page 202 the other day, belongs to what special family of ions? Darian? Yes. So a hydroxide ion is what we call a polyatomic ion. Did you remember seeing the hydroxide?
Yes.
Okay. What's special about polyatomic ions?
It's made up of 4 oxygen atoms.
But not always. because this has only got one oxygen and one hydrogen. Keep going. What else did you write?
The charge of a polyatomic ion is shared over the entire ion rather than
Yes. Yep, good. So our scribble picture, like that. Keep going.
That's basically all I have, but it said in the textbook that it's made up of four. If it said that in the definition.
So I would check that. Because polyatomic ions they vary. Here's an example of a polyatomic ion, an O and an H. Polyatomic ions can be a nitrogen and an oxygen, 2 oxygens. They can be a carbon and 3 oxygens.
It said, well, what I read was it said it was made up of more than one atom.
Yes, it's made up of more than one atom. That the oxygen and hydrogen, remember when you guys said about why doesn't the hydrogen leave? Why doesn't it just lose 2 hydrogens at the beginning? It's because this now is a hydroxide ion and it acts like one. This interaction between this oxygen and hydrogen with this extra electron is quite stable. No need to react. Okay? So the characteristics change for that molecule. That's why that other hydrogen doesn't get bumped out. Okay, so it stays, these polyatomic ions, really, if you see a polyatomic ion, typically we're not going to break the bonds in a polyatomic ion. Okay, so make sure you have that added, because we're going to have to start recognizing these polyatomic ions, because that changes the way we make our predictions. Sean?
It says in the textbook that the polyatomic ion, an ion made up of more than one atom that acts as a single particle.
Yes. Okay. We good? Okay, so back to here. If we look at now what we're going to write. So this thing, this cation is a potassium ion, and this is a hydroxide ion. Okay? So we call that molecule, does anyone have a guess? This thing has a name. Go for it, it's fun.
Which one?
Like the chemical formula?
No, what would be the whole name of K of this molecule that I've got chalked here?
A.
The name, the words, not the chemical formula yet. We're gonna get there. Guess. It's fun.
Hydroxide.
Cation hydroxide.
Cation hydroxide?
Yeah.
What's the name of the cation?
That's
Now you got it.
potassium hydroxide.
Yes, potassium hydroxide. Good job. Because there's lots of cations, we have to give its name. Potassium hydroxide, I'm just going to put this underneath, plus, so that's talking about this guy right here. What about this guy? Because that was also made. Can you see that okay? Good. What's that thing called? I already described it. Come on, guys. Celine, what's that thing called?
The hydrogen ion?
Nope. You got hydrogen.
Crystal
What state is it in?
after?
Bubbly, 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 bubbly. What did I describe that as? Number 1. Bubbles of gas. This is a gas, right? So we actually say hydrogen gas. Okay? So that's a story of, it really is telling a story. Equations are telling a story about what went on. Man, oh man, this does not do this very much justice, because the reaction that goes on here is quite complicated. The layers, this goes here and that goes there and this gets kicked out, and that's pretty cool. But so this is a very simplified version. So that's the first thing you're going to do. The second equation you're going to do is what I call a particle equation. Okay? Particle equations next. My short form is this. I gain for space.
I use
I can leave that up there for a little bit while I get organized here. So we're going to follow the same thing that we did with our word equation, but now we're going to show it in particles. Okay, particle pictures. Remember when we did our ancient C, same thing. I'm going to do it all in chalk because this is what you're going to be doing in your notes. So what does potassium look like? The particle of potassium was this. Do you remember I had these guys here? You don't have to do CVR. Okay. Let me just put a few. Well, actually, how many potassiums did I need when, actually not me, Holly, Melissa, and Julia, when they did this reaction, how many potassiums did they use? How many, how many were before, and then how many did they actually use for this reaction? Okay, how many did you use? You used 2. So I'm just going to put 2 here. Okay. Plus water. How many waters did they use? I think they used 2, didn't they?
Yep.
Our arrow, our during, what does it produce? This is the way we show potassium hydroxide. Yes?
Is it possible to send Skylar Gilbert and Terry Martin to the library for 2.8 seconds?
Sure.
Thank you.
Okay, how many potassium hydroxides did they make? And I could even put a little circle around here to say that's a polyatomic ion. They're going to stick together, just to refresh my memory. How many were made? Sean?
2.
2. How many hydrogen gases were made? How many H2? 1. Okay, there's my story. The next part of the story is our chemical equation.
Oh, no. I'll let you
Chemical equation? And this is when we get into things that are called chemical formula. The chemical formula for potassium is K. This is, I'm going to my periodic table now.
Oh.
And I'm looking at what is the symbol for potassium plus chemical formula of water is H2O. Gives us chemical formula of sodium hydroxide is KOH. What's really cool about this is it's looking awful similar to our particle picture.
Oh.
But this changes. What's the chemical formula of hydrogen gas? H2. So when you're dealing with chemical formulas, you've got these subscripts that start showing up. And that's just again a simplified way. Good? Is it on okay? Yeah. Simplified way of showing water. Instead of drawing out all these particles, we just show it in a chemical formula.
For the particle picture, you know how you had as many K's as you used and as many, like, you had 2 K's in that?
Yes.
So the chemical equation, why wouldn't you write like 2K, 2HO?
Well done. I love where your brain's at here. Okay? So this is what we call a skeleton equation. And what Nick was talking about was Nick is talking about the fact that, well, wait a minute, we used 2 waters, but that doesn't show that down here because we haven't done the next important thing about this is, who needs more time for the skeleton equation word? Okay. We have to balance it, so it's not balanced. Okay. How many potassiums did we have? Yep. sorry, Sean, 2. So we put this number in front of the number that we had in the reaction. How many waters did we use? 2. We put that number there. Okay. How many potassium hydroxides did we make? 2. We put that number there. How many hydrogen gases did we make? 1. We don't need to put the number there.
Oh,
So this chemical equation has now become a balanced equation. This picture, the power, I'm just writing this story in different ways. This is your answer. All you are then is becoming an accounting person here. You're counting things up, you're saying, what are my numbers, and you're putting together an equation. Any questions on that? Okay. The fourth equation that you're going to write is what we call a mass equation, and I'm not doing that yet because we do that as an experiment later on. Okay. Okay, so that's why this size of a recipe book is good. So here's an experiment, and they've got their 4 equations written. They've got their signs down here. They just put them in different order, doesn't matter. And they got their CVR of the products. Okay? And there's another experiment. And there's another experiment. And there's another experiment. Got it? See, they all follow the same format. But don't forget, you don't get to keep this. So it has to be in your notebook first. And we don't like to do it because, oh, why would I do it twice? Well, I love doing it twice because that's repetition. Okay? So here we go. Take out your recipe book, please. And we're going to go through now and I'm going to describe to you what the pages are so far. On page 1, we're going to title it the Physical Property Lab. So the first page is just going to be conductivity tests that you're just describing the results. It was a conductor, blah, blah, or it wasn't a conductor, and you're just organizing that. Okay? Page 2, reaction of the alkali metals in water. Here's what you need to do. I've already shown you potassium. Okay? I want you just to do sodium.
Record that.
Organize your username. What did I do? What did I do?